let me start with one of these. It's late 2024, and a lot of the AI applications that we have every day that you are using on a daily basis are powered by one of these. Now, this is, if you can't tell, this is what DALL-E 3 thinks a vector database is. I don't know if it actually looks like this. I haven't seen one look like this. But what you can see with this one is it's kind of juggling two different things. On the one hand, there are emails, and there are these shopping carts representing e-commerce use cases. And what we've seen is that while both use vector search and while both sort of work with vector embedding models, the underlying use cases are quite separate or quite different, and also the scaling challenges that come with that are quite different. So on the one hand, you have these single tenant versus multi-tenant cases. Sometimes you have billions of vector embeddings in your data set. In the other case, you have millions of data sets themselves. Sometimes you use in-memory stuff. Sometimes you run it on disk. Sometimes you care about query latency, cost, etc. And that makes it actually quite challenging. And basically, this talk is a summary of two use cases that we've worked with in the past that are running in production right now. And yeah, hopefully also to give you an insight into what you can do to structure your case successfully. Let's start with the e-commerce search one. So first up, from a user perspective, even though we're talking about sort of very deep in the stack and infrastructure layer, let's start at the top. How does a user actually interact with this? And here we have this sort of, again, DALL-E generated sort of mock e-commerce interface, and there's a search bar prominently in the middle of the screen. And basically, you would start out and put any kind of search query in there to find the kind of products. And this is relatively unstructured. There's not a lot of context. Yes, you could add faceted search or filters or so, but basically, if you look at how the data flows and how the data is queried, you don't really know a lot up front. So in this kind of data set, we're really just treating it as this one monolithic block. And if a query comes in, you don't really know where the query is going to go. You have nothing ahead. So if the query is a colorful summer dress, that would be in a very different section, so to speak, of the vector space than a professional video camera or something, which would be electronics related. So really, until the moment, and maybe this sounds kind of obvious, but until the moment that the user has entered the query, you actually don't have anything to narrow the search down. And you will see later that this isn't quite a bit of a contrast to the other case. So how does the data flow? For this particular case, what this company did is aggregate basically products from separate sources. So in this case, some example large retailers, Amazon, Walmart, etc. And you can think that all of these, they have a pretty large data set. They have a large amount of products, and they're constantly updated, etc. But all of these products are going into that same one vector space, and then users, when they query this, they don't care where the data comes from. They're searching for the best possible product, and actually one of the business values that this particular company provides is that it aggregates across those retailers. So this is specifically sort of a partitioning in the source data that is lost when we're looking at the user data. And then one of the challenges here is that, well, Amazon, Walmart, etc., there's lots of updates, lots of new products added, old products going out of stock, etc. And that on its own is a pretty big challenge at that kind of scale. What we try to achieve is the total number of objects, and therefore also vector embeddings that are attached to these objects, was somewhere between 1 and 10 billion, which is, if we're thinking back, so Weaviate is now about 5 years old or so, and like just 2 years ago, billion scale was just unthinkable in general. A million data set was a lot, and now we're talking billion scale. There are tens of millions of updates per day. I think the peak that we saw, and some of our SREs were a bit sweaty that day, was over 100 million in a single day. And that's quite a lot, especially if you've tried vector search yourself. You may know that an update on a vector index may induce an additional cost. The kind of query latencies that we want are basically as fast as possible, 200 milliseconds, 500 milliseconds, which if you've looked at a vector index benchmark, you may say, like, oh, that's actually pretty high latency. Like, we're talking single-digit milliseconds there. But keep in mind, the P99 is the P99. This is basically 99% of the worst queries, including filters, including faceted search, everything. And that's pretty ambitious to get this down to this kind of latency. And then I said, yeah, the data set there's really just one partition. So how can we find the right tech for this kind of data data set. Maybe you've heard of HNSW. HNSW is, I think it came out in 2016 or so, and it's kind of the state of the art, or even if you don't believe that it's the state of the art, then whatever those people propose is also a graph-based index. So it's very, very close to the state of the art or the state of the art, and it's optimized for very low latency and high throughput. It does that with a sort of layered approach, and this is kind of perfect for this case because we have a massive data set and we need low latency and we need high throughput. There is a downside. There's just no free lunch in engineering. It's always trade-offs, and it's an in-memory vector index. So you need to keep all of those vector embeddings in memory. And now we can think, if we're thinking of the regular text embedding 3, which is OpenAI's sort of most current vector embedding model for text, it has a dimensionality of 1536 dimensions. And now if we're taking 10 billion vector embeddings times 1536, these embeddings are 4 bytes large, then we're just ending up at 55 terabytes, which is a lot. And this is sort of ignoring high availability and replication. You probably want to run different copies of it. So this is just doing it once, nothing else, 55 terabyte in memory, which is not a small machine or not a small cluster. However, we can kind of work on this, and this is one of for me, it was one of the key elements in moving cases to production because cost efficiency plays such a large role in moving into production. We can use product quantization, which is basically a clustering and compression algorithm that we can run on the data set. And in this case, we could reduce the size 8-fold. And this is a lossful compression, but then you can make up again for the sort of loss in accuracy by re-ranking against the full-size vector embeddings. And those full-size vector embeddings are stored on disk. So you've basically traded off a bit of memory, which is very expensive, for disk space, which is a lot less expensive. And that helps a lot with those production use cases. And then if you've heard of HNSW, you may have also heard of, can HNSW even handle these number of updates or deletes? Will it stay fresh? And there are blog posts out there saying it can't, and that's almost true. If you look at the original HNSW paper, it really could not handle deletes at all. Like they would just basically be markers and then it would degrade over time. But we've built at Weaviate, we've built an implementation of HNSW, a custom one, that has an in-place batch repair job. And then which you can see in this graph over here, especially like at the top, the orange and green lines, is that over time with many cycles occurring, the quality does not actually drop. So this is recall in percent. It's basically 100% recall or close to 100 with the orange line. And even if you keep sort of replacing the data set through updates and deletes, the quality does not degrade. And then one of the things that we had to really improve for this particular use case was just the amount of it, to be able to handle millions of those updates per day or hour without giving up the quality. So in summary, for this first use case, the e-commerce case, we said very large billion scale data set. We want to use it. We want to use HNSW, which is an in-memory index. That makes it fast, but that also is very costly to build. So we need a lot of CPUs. It runs in memory, so we need a lot of memory. However, we also applied compression, so we could actually get the memory footprint down a bit. And then if you find a reasonable balance with the number of CPUs, that actually becomes a lot more cost effective. We're also using SSDs. Like I think no database can ever work without any kind of disk. We're making use of them, but you can see sort of they're not the main value driver. They're just basically the persistence layer, and we're using them for re-ranking. And then for completeness sake, we're also talking about object storage, which was actually not used in that case at all. And spoiler alert, this is a contrast to the other case that we're going to look at right now, which is email RAG. So RAG, retrieval augmented generation. The idea is basically if you ask a large language model a question that it doesn't know the answer for, it has two options. Either it needs to hallucinate and just make something up, which is not what you want, especially not if you're running it on your own email inbox, or it can look up the data from the actual data source and take that into consideration for the prompt. And this is what retrieval augmented generation is. And maybe a quick raise of hands. Does anyone use the email client Superhuman? Yes, I see. Oh, not that many, but a few. Cool. Do you also use the Ask AI feature in Superhuman? Yes. Perfect. Then you've used Weaviate. Yay. That runs on Weaviate. And this is actually the case or modeled after this case that I'm describing here. So for those of you that don't use Superhuman, you can kind of think of it like this, sort of an Ask AI assistant, where this is not the primary way you interact with the app. It's an email client, so the primary way is to write emails, etc. But maybe you want to ask it a question that is somewhere where the answer to the question is somewhere in your email. And then you get this typical Ask AI. I believe that's a name that's quite common. If you use Notion, for example, I think they're also calling it Ask AI, which is kind of this pattern of AI assistants that don't hallucinate, or ideally don't hallucinate, but base their knowledge on that data source, in this case, your email inboxes. And if we're looking at that kind of data set, you can think of this as the complete opposite of the one that we had just before, because you have many, many, many small partitions, and these small partitions are your individual email inboxes. If you want to ask a question about your mailbox, well, you really care about the answer that is in your mailbox, and you definitely don't want someone else to search through your mailbox. So putting that at scale, you can kind of think of the amount of objects or vector embeddings in a single data set is now much smaller. No one has a billion email. I hope you don't have a billion emails. But there are millions of users, and that's a completely different challenge from an architectural perspective. How does data flow in this case? So all of you, I guess, get at least one email per day. If you don't, then you're lucky. And possibly a lot more than one emails per day. But you might not actually use this Ask AI feature on your mailbox every day. You really use it when it adds value, like when is my flight out of San Francisco, something like that. So we have this kind of imbalance between the number of incoming writes, which is just incoming emails, and the number of user queries. And also we have this sort of partition of multiple data sets. And as I said, the user behavior is very sporadic. Scale is actually somewhat similar in this case. So we're talking about, again, sort of 1 to 10 billion. This is a bit more dynamic because it really depends on how many emails people are getting. The number of inserts is a bit lower. The query latency is kind of similar, the targeted query latency. You get away with a bit more because, of course, in a RAG workflow, which is not just search, you also have the latency of the large language model, which is often way higher than that of the retrieval augmented generation part, or of the retrieval part. So we get away with a bit more latency, but still it has to be real time. And then the interesting thing here is in Weaviate language, we call these tenants, basically the data set partitions, where we had just a single one in the other case. Right now we have hundreds of thousands, and this depends on how many more folks are signing up for both Superhuman and the AI assistant feature. Another thing that's very interesting is that those tenants, those email inboxes, are not equal. So some of you may be power users. Maybe if some of you work in sales, you probably send a lot more emails than someone who maybe works in engineering. And this is kind of, with these multi-tenant cases, this is very true all the time. You have a lot of very, very small inboxes, and then you have a couple that basically are much larger than the others. I'm just seeing on the bottom scale here, it says 1 million twice. The max is actually 3 million here. And what we can make use of this kind of, or how we can use that kind of distribution is by using what we call the flat index in Weaviate. So before we saw HNSW, this billion scale, very large in-memory kind of index, and now we're actually using a much simpler index, which doesn't use a sort of complex graph algorithm, but it's more sort of a linear scan, and it's just optimized for disk usage. And that in turn works super well because the data sets are so small. Small, again, sort of what we consider small right now is like 1 to 5 million or so, which I think just 2 years ago for vector search was basically the large data sets. And then we can again use compression techniques. In this case, we're not using it to reduce the memory footprint because the memory footprint is already pretty low, but we're actually using it to speed up the search, because if you do this linear search, if you have less data to search through, then the throughput is going to be higher. And this is binary quantization. This is one of, I believe by now it's 3 or 4, where we're adding more and more all the time, quantization options in Weaviate that give you that kind of flexibility. Another thing that you see here, which is very, very natural in pretty much all use cases, but especially in these multi-tenant use cases, is that the number of user activity very much sort of flows. We have these highs and lows, and for emails, this is mainly just sort of Monday morning, 9 a.m., everyone uses their email client, and maybe on Sunday, hopefully not as many people do. So we have these natural fluctuations, and we can actually, again, make use of this by sizing our infrastructure for the amount of tenants and users that are actually active rather than the ones that are inactive. So just because you get an email in doesn't necessarily mean you need your vector embeddings in the hottest cache layer, which would be memory or maybe SSD drives. Maybe if you're inactive, if you're not even logged into the email client right now, we could also just put them on cloud storage, which makes it a lot cheaper, but of course also comes with a latency kind of trade-off. So in summary, for this second use case, the email RAG use case, we don't really need a lot of CPUs in this case because the indexes are relatively simple. They're disk-based, they're often I/O bound and no longer compute bound. We do need a bit of memory because it's still software. Software runs somewhere in memory, but we need a lot less. It basically acts as a cache, and you can just add a bit more to speed things up and basically right-size this way. The bulk of the work is handled by SSD drives. So this is really very much a disk-based kind of case. And then you can see also, as we just said, sort of everything that's not active, we can also offload to cloud storage. So you may say right now, well, could we not sort of turn this around? Could we not run primarily on cloud storage, on object storage in the cloud, and reduce the number of SSD disks as well? And that's actually a very good point that I'll get to in a second. But first, looking at those two cases, where do they overlap? And one of the things is just the massive amount of scale, 1 to 10 billion number of objects and embeddings with a sub-second latency. And it's a very different composition of those data sets, but in sum, basically, they're both very large and they both had their very unique challenges. Another thing that you get with Weaviate out of the box is the interaction with those embedding models. So in this case, one of the cases used OpenAI, and I think the other one used Cohere. And when we shipped this feature initially, it was very, very simple, like way back. It was basically just you interact with Weaviate with your natural objects, in this case text. I think image embeddings are not used yet by either of those two users, but Weaviate does support them. And it would just send them sort of to the model, and the model would send it back, and then you would get the embeddings. But by now, this has actually grown into some pretty serious tech, because working with the different rate limits of these kind of things. So Cohere, for example, has a rate limit on requests, and then has a number, sort of a limit per request. OpenAI has a rate limit on tokens, and just those two and switching between the two is already a lot of effort. And that's why I put these real, actual snapshots there from our observability stack, basically looking into this, because this is kind of work that you don't have to do anymore. It's not so simple as just send it to the API and you get the vector embeddings back. Doing that at this kind of scale, you really need to optimize for it, and this is what Weaviate does for you in the background. So what's next? I'm not going to give you the full roadmap. If you're interested in, you can find that on our website. But since we just talked about the cloud storage part, one of the potential limitations, if you can only offload something that's currently inactive, would be that, you have this split between the write path where you get a lot of emails, but you're not querying them. So is this now active or is this inactive? And this is exactly what we're trying to solve with a full separation of storage and compute, where we're splitting the write path from the read path and making sort of cloud storage the source of truth. And then if you get 1 million emails, but you never query them, then basically we never need to load it into the serving nodes, which have the SSDs, which have the memory. And that, we predict, will give another 2 to 3x cost reduction for, especially for these multi-tenant kind of use cases. So to recap, we've looked at 2 billion scale cases, both running in production with Weaviate right now, both requiring real-time latencies. The first one, the e-commerce case, has this single data set requiring high throughput, low latency, which is why we went for the HNSW index. We used compression to reduce the amount of memory footprint, but it's still sort of an in-memory use case. And then the other one was the email RAG case, where we had hundreds of thousands of partitions that are all relatively small in comparison, which allowed us to use separate indexes that are disk-based. And if you're interested in sort of how we're managing so many different partitions at scale, then I can refer you to my AI conference talk from last year, because that was on how we're doing multi-tenancy in Weaviate. So how can you learn from all of this? If you have a vector search use case and you want to move into production and you want to do this in a cost-effective way, the first question to ask is, what are those natural partitions in your data set? Are you like the e-commerce case where there are no natural partitions and you would basically set yourself up for failure if you try to do those partitions because a typical query would go across all or most partitions? Or are you like Superhuman, the email rack case, where you have these natural partitions, which in the case of email is different mailboxes, where basically you know up front what the query is going to be? That was my talk, but before I wrap it up, there's actually something that I want to share with you as well, which is my Gen AI blooper reel, because I included lots of Gen AI images in here, and of course I took the ones that worked out, but not everyone did. Here was one of my early attempts where it kind of like this. This was basically the e-commerce app, and I liked it, but it really mentioned the word e-commerce search too much, so I asked for it to reduce it to just once, and it said, well, here's the revised mockup with the words e-commerce search mentioned only once in a central place above the search bar. No, it's not. This one is also really great. This was supposed to be my title slide, but I really wanted something neutral in the middle, because like this whole talk has on the one hand the e-commerce and the other hand the email case. So I wanted something neutral like the database in the center. So I asked for something neutral in the back, in the middle, like a database. The shopping cart in the center has been replaced with a neutral, abstract, and futuristic machine symbolizing a database. Nope, I think that's still a shopping cart. And here, this is my favorite one. You've heard it here first. So new tools in AI, the new trends are pupurtion, normation, boperation tools, and tropestion. Don't ask me what those are. I have no idea, but I'm sure they're going to play a large role in AI in the future. Thank you so much. Any questions?
Any questions? Sorry, I'm in the back. If you have questions for Etienne, please raise your hand, and Guy will come to you with a microphone.
Hi there. Thank you very much. It was a very interesting presentation. I wanted to ask, how do you prevent leakage between tenants, especially in email? It's very sensitive. How do you make sure they don't overlap and you don't read somebody else's email? Thank you.
Yeah, great question. We're actually separating tenants completely separately, so they're completely separate indexes. So these are not shared indexes that are then broken down, for example, by filters, but they're basically they're separate folders on disk. Or you could, if you wanted to go even more extreme, you could potentially have completely separate disks. But basically, there's nothing shared in between. It's only sort of it's not even aggregated, but it's basically only served by the tenant ID at the API level, and in the persistence level, it's completely separate.
Yeah, with regards to the e-commerce data set, I mean, a lot of e-commerce gets done in categories, right? So doesn't that form a natural partition, like books versus electronics versus apparel?
Great question. And this is something that internally we've also discussed quite a bit. Would we benefit from splitting this up into the main categories where we know that the user will put a category filter on it? Or this could either be something user-facing, or this could be something that internally in the business logic where you would maybe separate it by the source or so, because you get better commission on one of those retailers than the other, so you maybe want to push those and exclude the others. And it's a trade-off. The cost goes up for the unfiltered query that really goes across the entire data set, because now you have to search across all those partitions. And especially the HNSW index is more efficient with a single data set than it is searching through multiple in parallels, because it scales sort of logarithmically. And it's a trade-off. You could go for maybe 10 separate partitions and say, okay, if we really get an unfiltered query, we'll just run for 10 of those partitions in parallel, but that also essentially means your QPS is 10x higher in that case. So it's a fine trade-off, and I don't think there's any one right answer, and this might also still evolve over time. Thank you.
Sort of related question. At what scale for the use cases where you are partitioning do you start to consider like sub-partitions where maybe one partition is so big that trade-off starts to be worth it?
Yeah, that's a really great question too. It's something that we've also talked about quite a bit. Right now, we've kind of gotten lucky in the sense that most cases are small enough to still fit in a single partition, but we don't expect this to be the case, because right now, again, sort of, yeah, the 1 to 5 million or so per tenant is still fine for a single use case, but this is probably going to grow in the same way that 2 years ago, 1 to 5 million was a large data set. So still up for debate, but yeah, we'll see. This is definitely something that's coming too. Thank you. Another one there.
Hi.
If you have a question, to make sure you make eye contact with the guy who has a microphone. Thank you.
Hi, my name is Reza, and thank you for your presentation. I really like that. You said that the heart of your algorithm, a portion of that is HSMW, which you use for a graph base to do the search. My question is one step before, which you create the vectors, and then also it's a graph base. So could you please provide more description about how did you choose about vectorization? I know that you provide several explanations about OpenAI or others, but a little bit because you use different modules, I just feel lost. So it would be great if you can detail about vectorization and also the part of how you shape that graph when you want to use SHMW. Thank you so much.
Yes, that in its own could be a full talk. I'm going to try to give you a one-sentence answer, and I think it really depends mainly on what you're going for. Some models are better in specific domains, so you could say, for example, I don't know, maybe Cohere is better in e-commerce, and OpenAI is better with the ambiguity in emails or so. Something like that. So you need to just run tests on what are the best one. But of course, also commercial aspects play a role. Like at that kind of scale, you're paying a lot of money just for the vectorization. So if you get a better deal with one of those providers than with the other, that certainly plays a big role. So it's kind of a trade-off. Like, are you going for the best possible accuracy, or are you going for other business metrics? And of course, also very important, it's a very, very fast-changing space. What could be the best model right now may not be the best model tomorrow. And then, of course, also very important, there are a lot of open source ones that also change very rapidly. But if you look at the leaderboards for vectorization, often open source models come out on top. And then if you run them yourself, it's kind of, again, a trade-off. Do you really want to host a model yourself? If yes, then you can probably get the cost down quite a bit. But you also have the effort of hosting it yourself. Or you could wait for Weaviate to offer model hosting in the very near future.
2 more questions, one standing and one in the front.
Hi, so I'm a Weaviate user. Yeah. So I just have a quick question. I wanted to know what was the reasoning behind the change in the API from V3 to V4?
In the Python client?
Yeah.
User experience. We got a lot of. Are you a fan of V4, or are you?
I just read a little bit about it. I'm using V3 at the moment. Just.
Okay, gotcha. So really, I think. The real answer is V3 was very Weaviate driven. We were looking at the Weaviate APIs and we're just thinking of like, how can the client represent our own APIs? And V4 was very user centric. We were looking at how do people use Python clients in general? Can we make it more Pythonic? Can we sort of identify workflows that are maybe very verbose? And even if they require multiple steps in the APIs, could they be sort of simplified in the client? And another one is also performance. For sending a lot of data over the wire, especially like uncompressed vector embeddings. REST APIs are often not the most efficient, and the V4 fully supports a gRPC, which helped us quite a bit.
Hi. Now, quick question for the e-commerce use case. Are you using some sort of synthetic tags for the categories, books, etc., and putting them back in the embeddings, or anything else?
So do you mean synthetic tags like
Books,
categories, basically?
Categories, yeah, categories.
Yeah. So the full object with those labels, basically with those metadata labels, is ingested as well. This depends a bit on sort of what it is that the individual sources provide and what information you want to store. But yes, it is fully indexed. So Weaviate actually indexes everything that you send to it by default, which at that scale can definitely become a bit of an issue if you index something that you don't use. But yes, everything is there and it's indexed by default, and you could put arbitrary filters on it, etc.